good. So let me start the timer. This needs to be fast. So Filippo Mantovanni from the Barcelona Supercomputing Center. That's the place in which we have a big supercomputer. Okay, so I put it here because first you see the ratio of the computational power over time. This was the installation in 2004. This is the computational power compared to that 20 years later. So this is just for you to know where I come from and what we care about. That is mostly the flops, the performance. Okay, so try to think about the performance because it's one of the things that we care. The other thing that we care is we need to be able to port our system software for high-performance computing, for scientific computing. Okay, so we cannot afford to reinvent science every time that there is a new machine or a new instruction set coming in. Okay, so these are the two important messages here. So now I'm part of a European project that is called EPI, European Processor Initiative, that has two missions to deliver an ARM-based CPU and a RISC-V-based accelerators with 3 accelerators in it. So today, of course, we are going to look into the right part of this slide. I told you I was speaking in plural because within this chip that is actually taped out, and it is, okay, let's wait. They are excited because it's actually below this fan here. We have 3 RISC-V-based accelerators, okay? One is called Vectile. It's really cornering around us, so. It's a competition in noise, yes. So 3 RISC-V-based accelerator. One is the Vectile, that is a scalar RISC-V core coupled with a vector unit. Then there is the VRP, that's and the STX style. The VRP is developed by CA. I know that there is, yeah, you're here. He has a full talk at 2, I think, in the Alphas 2. Okay, so if you are interested in the middle one, he's your guy. And the STX accelerator that probably they can explain more detail in the ETH booth as well. Today we're going to talk about the Vectile. What you are going to see is a demo about this tile. We have a semi-dynamics core connected to a VPU, a vector processing unit, that is developed by BSC. Then, of course, to have the full chip up and running, we need some caches that are provided by Fort and Chalmers, partner in the project. And then we need some network on chip that is provided by Extol and a SerDes, because you will see we don't have a memory controller on chip, so we need a high-speed link to get outside the chip to get the data to and from the memory. And then we have Fraunhofer as a partner that has been the back-end partner for doing the silicon, and E4 that has contributed in the integration of the boards and the system. So this is the family picture, say, technological one, okay? But the important point is this one. This is a RISC-V chip that has been taped out and is up and running in the booth. I didn't brought it here because it's 20 minutes disassembled, 20 minutes assembled, and I have only 6 minutes left, so it wasn't worth it. But I invite all of you to come there, and you can play with what I'm going to show now. So special thing is the vector processing unit we do have. That is a wide vector unit. So you are probably familiar with the Intel AVX 512. So you can operate 8 double precision elements with one instruction. Here we are operating 256 double precision elements in one instruction. So the ratio is this size of data versus this size of data. Okay, so it's really a wide vector unit. That means that one vector instruction instantiates a lot of work, if it is to the memory or an arithmetic instruction. But that's the message. So the hardware setup that I wanted to show in the demo is composed by the EPAC that is running the VEC accelerator, so the RISC-V scalar core plus the vector unit. As I mentioned before, here we don't have a memory controller, but we have a high-speed link, right? So we have this companion FPGA that gives us access to the DDR that is on board. So basically, we have here our CPU, here our main memory, then we have an Ethernet link, and here we have our, say, support PC that is giving us the Linux kernel and the kick to boot the operating system. Okay, so you can imagine that everything is booted. We offload the Linux kernel, we boot, and then we have on the European technology RISC-V CPU that we did, a standard Ubuntu Linux up and running. Okay, so this is a great milestone for us because it's really a big achievement. Okay, and it's a standard Ubuntu Linux, so it's not a custom one. So we boot Linux, and starting from there, I jump now to the demo. I saved you all this process just because it's slow and boring. But in the booth, if you come, we can also show you the booth, the boot of the operating system and so on. So, and now I have a couple of minutes to show you. OK, so I show you that we have an Ethernet. So through this Ethernet, I'm now connected to a VNC desktop. OK, so this is the desktop of the RISC-V CPU that I mentioned, connected to the VPU. OK, so if I do cat pros CPU info, here you have the command. You see that the ISA, the RV64, blah, blah, blah. And here you have the V, because we support the vector instructions, okay, vector extension. And you see that the microarchitecture is EPI, the name of the project, and the Avispado is the name of the core by Semidynamics, okay? So here you have each top up and running. Here you have a shell open, and I can list my file if you want. Sorry, that's a typo, but it works. You see, I can list my file if you want, and I have my home directory of our system in our data center that is connected here, mounted via NFS. So standard tools from a data center point of view. Okay, so I can run my application. Right now, I have a graphical interface up and running just to be friendly, say, with the users. I mentioned before this is a standard Ubuntu Linux, so here you have all the tooling. So this thing is now running at 300 megahertz. I didn't mention this before. And one core at 300 megahertz. And so, OK, I really don't do the demo of Ubuntu, right? So let me jump to the this graphical interface. That is what's important for us in the, say, in the field of scientific computing or parallel computing, right? So here in the demo, we decided to show you some code that are relevant for the scientific community. In this case, there is a sparse matrix times a vector. This is a typical kernel that is using a lot of time in HPC. Sorry if I'm being too basic, but I want everybody to be more or less on the same page. Okay, so you see that there are yellow dots because we are trying to mimic the sparsity. Right now, we have a sparsity parameter here that is 0.6. If you want, I can change it. Let's put it, I don't know, 0.5, whatever. So this will generate a new matrix, and then we can run this scalar. And here you have the time, the execution time, and the number of megaflops that we achieve on our scalar CPU. Remember, we are not using the VPU right now. Now, if I run it vector, here you have, well, in this case, with this randomicity, say, you get 18x speed up, OK? So this is just a visual way to show you the impact of having a wide vector unit coupled with a RISC-V general purpose core, OK? So like this one, we have several other kernels. We have support for other libraries, but we are also testing real scientific codes coming from scientific communities like plasma physics, computational fluid dynamics, and so on. So this is really a RISC-V-based platform that is getting into science through this research project. I think I finished my time. I would be very, very happy if you pass by our booth and you can play with this. I just showed the SPMV, but we have a lot of other codes. And I don't think we have time for questions, but please step by.